Hello everyone and welcome. Welcome to this new webinar by iXblue Quantum Sensors, a division of iXblue Group. Welcome Camille, good morning. Today we are here to discuss sensing, quantum sensing, and we will discover with you, Camille, a new instrument, the Differential Quantum Gravimeter, or DQG for short, which opens exciting perspectives. It's full of exciting science, new applications, and new results by our company. So my name is Lautier-Gaud. I am the head of business development and sales at iXblue Quantum Sensors. And I'm very lucky to welcome Camille Janvier, the lead engineer on the DQG, which is the perfect person to discuss this topic today.
Thank you.
Before we jump in the details, the performances, I'll say a very quick note about our company, because we were known as MuQuants, a French company founded 10 years ago and specialized in quantum sensing. And last year we joined iXblue and became a division of iXblue, iXblue Quantum Sensors. And our activity is divided in 4 main pillars. We are very well known for our quantum gravimeters, the absolute quantum gravimeter. We also provide an atomic clock for time and frequency metrology, and a wide range of photonic solutions for high precision measurement, metrology, and quantum technologies. But obviously today we will focus on gravity sensing. And as we say gravity sensing, Camille, can you, for example, start explaining us what's the point of measuring gravity?
Sure. So gravimetry is the science of measuring the acceleration of gravity, small g. And this acceleration is an image of the force that pulls you downwards. So it is generated by all the masses surrounding you, and depending on how finely you can measure this acceleration, you will know more and more fine information about this mass surrounding you. And this is very well illustrated by this graph from the European Space Agency. So small g on Earth is about 9.8 meter per second squared. This is the result of the overall shape and density of Earth. But if you are able to measure to the second decimal, you will be more sensitive to the overall shape, the difference between the perfect sphere of the Earth and the fact that the Earth rotates. If you go to the third digit here, you will be sensitive to mountain ranges or to oceans. And if you go down to the 7th digit here, you are sensitive to large buildings around you, so smaller masses at shorter range. And the AQG, the gravimeter already commercialized by iXblue Quantum Sensor, is capable of measuring down to the 8th digit, so 1 digit more than is shown here. And this is about 10 nanometer per second squared, or 1 microjoule. And the use of a gravimeter, for instance, you can use it as shown here. So if you place it on top of a cavity here, if the cavity is empty or if it's full, you will measure a different value of G. The value of G when the cavity is full will be larger. And so depending on the measurement of G you get, you can know information about how this cavity is filled or not. But today we will talk also about gravity gradients. So gravity gradients are the vertical variation of gravity, so how gravity changes with altitude. And the units for that is the adverse, and it is about 0.1 microjoule per meter. So a variation of 0.1 microjoule on 1 meter elevation, which is a very minute change. What you need to remember in a nutshell is that gravity acceleration G is better for measuring larger masses at longer ranges, while gravity gradient, so gamma ZZ, is better for smaller masses at shorter range. And now Jean will tell us more about how do you use, how how do you use a gravimeter in practice? How is it useful for practical applications?
Indeed, and as you said, the DQG is an exciting instrument because it measures both gravity and gravity gradient with the same device.
Yes.
We can picture the use case on these schematics here. We can anticipate deployment on the ground as it is shown. And we can consider two main use cases. Either we displace the sensor on the surface by measuring over a grid of points, and we can retrieve sort of gravity map to infer the mass distribution on the ground. Or we can measure at a specific location over time, or come back at this location every year, for example, and then we can access the temporal variation of this mass distribution, as you say, if a cavity is filling up or is getting empty. With these two use cases, we can divide the main applications within three main areas that we can describe by looking at the depth at which typical sources occurs. The DQG is particularly relevant to spot and monitor shallow sources and sources that can be small as well. For example, a cave or a small void. Here the application is clearly in the context of civil engineering. For example, if you want to look and monitor the apparition of a cavity under a critical infrastructure, or if you just want to check that the integrity of the foundation of a critical building, for example. In the context of security of defense, it's also useful to use the DQG to spot unknown underground facilities or tunnels. And in civil engineering, it's also the idea of spotting and retrieving old infrastructures that got forgotten and that were poorly reported in literature. If we go deeper, so shallow means in the order of 1 meter to 10 feet. If we go shallow, deeper, we can access tunnels, for example, in the context of mining industry. And if we go even deeper, we can access details of ore deposits or reservoirs, and this is in the context of natural resources exploitation. That can be up to a few kilometers. If we look at the typical signatures of such sources, and I'm spoiling a bit the suspense, I apologize, we can say that the DQG has a measurement resolution in the order of 1 adverse, and you explain us what is an adverse. We compare this value, this typical resolution value, to typical sources, and tens of adverse for a cave, hundreds of adverse for a tunnel or deposits. So we directly understand that the DQG is really relevant to spot and monitor over time the integrity of such sources. So this is a general layout of all the applications, and now we really want to know what's inside these boxes and how does it work.
Yes, so I will explain this now. So here is a picture of our prototype for the DQG. It is composed of two big ensemble. On the left you have the sensor head, which is where the physical package is and where the measurement of gravity occurs. And on the right part you have the laser and control system. So in this box you have lasers, amplifiers, electronics, control like computer controllers and so on. And on the left part you have a vacuum chamber and ancillary systems. And so the way the DQG works is by measuring gravity at two different heights. So you can see it as two gravimeters stacked on top of each other. It's a bit more than that, but in principle it works this way. And the way we measure gravity, well, we perform a Newton experiment. So imagine the apple that falls down. You measure the acceleration of this mass, and you get, well, gravity acceleration. Here we are not using apples, we are using cold atom clouds in vacuum, ultra-high vacuum. And so a measurement cycle works in 3 steps. In the first steps, we trap the atom on the top of each interferometer, and then we let them fall, and we measure the acceleration during this fall. The result is a measurement of two values of g's about 1 time per second on this device. And from that, we can get access either to gravity acceleration, which would be the average of the two, or the gravity gradient, which is related to the difference of the two measurements of gravity. So the device itself is about the size of a person. It's about 70 kilograms for the sensor head and about 1.70 meters. The laser system is about 30 kilograms, and the power consumption is fairly reasonable at 200 watts. Typical sensitivity for gravity is about 60 microjoule per square root of Hertz and a long-term stability of 1 microjoule. So this is very comparable to what we already commercialized with the AQG. And on the gravity gradient, the sensitivity is typically 60 Hz per square root of Hertz with a typical stability below 2 Hz. In more practical terms, this means that if you want to detect a 1 cubic meter cavity close to the surface, I will come back to this later, but with a good signal to noise ratio, this will take about 1 hour if you had just gravity. But if you have gravity gradients, it's only taking a few minutes per point. So this really shows how gravity gradient can be useful for shallow anomalies. But there are also many different types of anomalies for which either having a gravity will be more suited, or having the two actually will provide more information. I'm thinking typically what you told about ores and reservoirs. Typically, in this case, having the two information at the same time, and I insist on this point. This is a simultaneous measurement of the two quantities will provide more information. I will focus more now on this case, so where the gravity gradient is more interesting, more useful. This is here what has been done here. So this was the first outside measurement done with this DQG. It is a lab instrument. So this was a challenging experiment to do, to go outside with this device. But everything went very, very well. And the idea there was to measure a cavity like this one, which is 1 cubic meter, about 1 cubic meter, with a small quantity of water at the bottom. There is a shaft and two manholes, one manhole. Actually, there are two cavities, one next to each other, and we measured in this direction, so transporting the sensor head on top of this cavity. And here is the result. Here in green are the data points for the gravity gradient. So here the amplitude is about 60 Hz, and each data point was about 10 to 40 minute integration time. And you can really see the anomaly here. In black, it's the modelization that we've done by measuring actually the physical size of this anomaly, this cavity. And this was really a proof of concept experiment that showed that we were actually able to measure with something that is fairly small in terms of geophysical anomalies. So now I will let Jean tell you more about what are going to be the perspectives for the DQG in the very next few months.
Thank you, Camille. Thank you for explaining the principle and for showing such results. This is really great to see. We understand today that the DQG is operational. We demonstrated a prototype that meets its goal specification. It went outside to take some preliminary measurement on a real use case, yeah. So this is really great to see. And we understand that this device is now industry grade, and we announced that it is commercially available. So should you have questions about availability, about the services brought by iXblue, feel free to contact us. The team is also ready to discuss your applications, to further discuss the results and the performances. And for the lucky of you who are attending the next European Geoscience Union General Assembly next week in Vienna, Camille Janvier is having an invited talk there where he will present even more results. And if you don't attend, no worries, we can still send you the result and discuss them with you. Thank you for your attendance. Thank you, Camille.
Thank you, Jean.
We will now welcome questions. You have the chat box in the web page that you can ask questions, and we will welcome them now. Thank you.
Thank you. So I see there was a question from Mark asking about so this picture. So indeed, the scale is around 3,000 adverse, which is about the say the natural gravity gradient of Earth, and the DQG is indeed an absolute gravity gradiometer. The accuracy budget is yet to be accomplished for this instrument to make it a perfect absolute gradiometer, but it is going to be done.
Yeah, and within the same package you have one absolute gravimeter.
Yes.
One absolute gravimeter, and you access the two simultaneously.
Exactly.
And to the best of our knowledge, this is the only technology that helps to have absolute measurement recorded continuously over time for periods of months, of years. So that really opens new perspectives for geoscience.
Yes, indeed.
Oh, Jamie is asking about the price, I guess. How much is a DQG? I'm suspecting this is a price-related question. This is the kind of discussion we prefer to have with the dedicated discussion. So I'm not going to announce any price tag as of today, but we will be glad to discuss these details upon specific requests. If you want still a broad range, it will be below 1 million and more than 500,000. That gives you a very broad range. And for a more focused estimation, feel free to contact us.
Christian asks if the DQG can measure the other component of the gravity gradient tensor. No, not in the same way. You can actually move the sensor head around and then measure from that the gravity gradient in the x and y direction, but it is not made to measure at the same time all these components. The issue to do that would be that to make this would increase the complexity of the sensor quite tremendously. So the choice has been made to only measure gamma ZZ.
Okay. Leonardo is asking, I was expecting a sensor that could fit inside an AUV. Is any project to reduce the dimension of the prototype? Tell me, what's the perspective?
Yes, so it's actually the goal of a European project that has been awarded to a consortium including iXblue. iXblue is leader actually of this project. So it would not fit, I think, inside the AUV, but we will reduce the dimension of the sensor indeed. This is part of the goal of this project, which aims at having a field compatible, fully field compatible DQG, and the idea would actually to lift the weight, the actual weight from a user-operated DQG to a more autonomous version with a mechanical advantage here.
So all of this integration on a moving platform will be achieved during this project you're referring to?
Exactly.
When is it starting and how long will it last?
It's starting soon, probably in the next few months, and it will last for 3 years.
Okay. Okay. If we can complement on previous questions, maybe we can still give some rule of thumb about the dimension of the sensor head, because with this physics, the dimension sets the sensitivity of the measurement. So at some point, if we want to shrink the size, we can, but we will degrade the resolution capability. So it's always a trade-off.
Exactly.
Should we want the best sensor on the ground, on the Earth, but not being able to move it? or should we want to set it in a shoebox, but basically measuring nothing? So
yeah, exactly. So there are tricks that you can play with to increase this sensitivity, and we will try a few of them. But yeah. Anyway, all thing equals, like the sensitivity is directly the height of the device.
And on an application perspective, it was a choice
yeah.
to make a device resolving one adverse
yeah.
for typical this application. So it means that the size is as it is,
exactly.
roughly speaking.
Yeah, exactly. The trade-off was to make a device that is small enough to be handled by two persons while still being able to measure relevant signals. Because, yeah, as you said, you can make something very small, but not interesting for applications.
So a question from Guillaume, how do you differentiate between size of the cavity and distance?
This is a tricky question. This is difficult, in fact. So here, in this case, we knew what's the size of the cavity. So in this very specific case, it's straightforward. In practice, I believe that you can use both gravity and gravity gradient. If you have a good signal and a good enough signal on gravity, you can probably set boundaries and even to estimate the size and the distance. The size will be related to the size, the width here of this anomaly, well, the lateral size at least, and the distance will be between a comparison between the signal and of gravity and gravity gradient,
okay.
I believe.
And here we are clearly addressing the value of the DQG to measure both quantities at the same location and at the same time.
Exactly.
Okay. Dan, how do you maintain verticality during measurements, and do you correct for it?
During the measurement, the device is stable enough to remain vertical. We set, so we have a sensor to set verticality the same way as the AQG actually. We set the verticality of the instrument before the measurement. And then if there are alterations, we use this sensor to correct for it. But I want to point out also that the gravity gradient is actually not that sensitive to verticality. It is sensitive, obviously, but not that much less so than gravity. The reason being that the gravity gradient that you measure is about the resolution that you're looking for the gravity gradient is 0.1 part per thousand, while for gravity you're measuring at 1 part per billion. So then verticality doesn't play in the same way in this case.
Okay. Question from Ben. How does the device behave in terms of drift stability compared to Lacoste or Sintrex field devices, for example?
I believe that you mean by Lacoste and Sintrex field devices, you mean...
These are relative gravimeters.
Yeah, relative gravimeters. It's not about the absolute gravimeters. No. So obviously this is an absolute gravimeter and gravity gradiometer, so the drift is very small. It's actually non-existent. So the long-term stability that we mentioned before is about that. Is 1 micrograd for gravity and 1 or 2 adverse for long-term stability in this kind of applications.
This is the typical data that we can also discuss with you if you have specific requests. I don't know if you have that in this presentation, some time series of a few weeks to show?
This will be shown at EGU.
At EGU, okay, great.
What is the difference between the height between the bottom and upper absolute gravimeter? It's about half a meter, a bit more than that. This is the order of magnitude.
Okay. A question from Jamie, will the DQG be able to take measurements on the move when on the platform, or will it have to stop and measure?
It will have to stop for now. Having an instrument that measures on the move is a very challenging thing to do with the cold atom technology.
With any kind of ballistic technology.
Yeah, exactly. Any kind of, it would be the same with a corner cube, for instance. The idea is simple: is that you need to move less than the size of the vacuum chamber your mass is dropping in. So this is the zero level requirement. Then there are all complexities you can imagine. So right now we are not planning we are not working actively on the idea of having something moving on a platform, but yes, I hope in the future we will work on it, because it's a very interesting aspect, and there are solutions to work with that, but they are on a different compromise of trade-off of like engineering trade-offs are different between a static measurement and a moving measurement. So.
And this is what you will do in the soon to come European project. You will integrate a DQG on the terrestrial drone.
Yeah.
It will move, stop, measurement, and go to the next.
Exactly. Okay. So it's not going to measure along the movement. It's going to be it's not possible as of today.
To give you perspectives, we can comment on results gotten by Onera in France about putting such technology in a moving platform. So this was done for a gravimeter, so measuring small g. The Onera team was pioneering to put such device and technology in a ship for a seaborne application, and in a plane, in a flying plane. They got actually really exciting results that got published. And with iXblue, we are now collaborating with Onera to produce marine gravimeters that will be delivered to French Navy in the years to come. Yeah. So putting such technology on a moving platform is possible and has been done, but the fundamental limitation is actually the test mass not hitting the walls of the device.
And as you said, since the sensitivity of the device is related to its height, the longer the device, the longer the atoms have to fall, and this will increase a lot the requirement for airborne or seaborne measurements.
Question from Olivier: what is the sensitivity of the DQG measurements to the verticality of the system setting, especially when you have to move the system at different positions?
So I'm not sure I understand exactly the question. So ideally, so again, for gravity gradient, you're not that sensitive. You're a bit sensitive, but not as much as gravity. For gravity, without without post correction, you need to be within 50 microradians to verticality to ensure a good quality measurement. Without that, I'm not sure. I don't want to say anything that is not correct. I think you should ask probably. We should ask the engineers working on the AQG, which have a more. So in general, moving position to position, it's not that difficult to be anywhere within 50 micron radians of the verticality. This is not that difficult.
Okay, thank you. And another question from Premislav. Question clarification: what is the height above ground level for the bottom and upper gravimeters? Okay,
I have not this exact measurement in my head right now. I would say it's about. So for the bottom, it would be probably 70. Okay.
Could you explain on the schematic?
Yeah. So I can try to. So the question is about what is this height with respect to the ground. So I would say this height is about 70 centimeter, but your question is related as well to to the fact that the measurement height is not exactly where you start your free fall. So right now I don't have the answer, but we can discuss later, I think, about this question, because also it encompasses specific details on the way the measurement is done, which I have not, for the sake of simplicity, described here. So the question of the measurement height is a bit different in this instrument than it is for the AQG, for instance. But I think you can contact us and we'll discuss this later.
Definitely. A new question about on the road being field compatible. Is the sensor isolated from environmental influences during measurement, including temperature and vibration?
So temperature, no. This is
not yet.
Not yet. This is why we said this device is a laboratory device for now. Although we will work on it. For now, it's really made to be in a rather temperature-controlled environment. Although it's not that sensitive, vibration it is. It uses the same active compensation that the AQG, which relies on the measurement of the acceleration between during the fall and active compensation. So yeah, to some extent, actually, you are not able to. We will not be able to measure during like on a car, for instance. It won't be possible, but still in a quite noisy environment. Currently, the DQG is operated at the second floor of a university building with a tramway going like a few hundred meters from there. So it works pretty well.
Mm-hmm. And I'm anticipating the next question about temperature. Will this device operate both in the desert or in the polar regions? You explained very clearly that this is a first version which is made for indoor measurement. Yeah. And to complement that, we can leverage on iXblue experience of the AQG, the field version of the AQG-B, that is now produced routinely. This device is field compatible. It has been deployed on the summit of a volcano, of an active volcano in Mount Etna in Sicily. It has been deployed in Antarctica, so polar regions. It works, and we can expect the same. I guess this is a question for you. Can we expect the same level of maturity of the technology for this particular device?
I think so. I hope so. Mm-hmm. Only experiment will tell. But yes, there is no fundamental reason for it to be very different. But again. Only time and actual measurement will tell us this.
We need to demonstrate.
Yeah, we need to demonstrate.
There is a really sound foundation for good hope.
Yeah, and I think so. Yes, and I think it's also in the culture of iXblue quantum sensor to try to test things as much as possible. Mm-hmm. Yep. So this question.
So I think that was the last question. We still have time. I mean, we are here for you. So should you have more questions, feel free. If the question comes after a good night of sleep, no worries. We can answer that by email. And then Przemysław asking.
Yes. So does the drop takes place at the exact same time? Yes, it does. It's how we make this simultaneous measurement. It's important that it does, and the way it's ensured is the fact that both interferometer use the same laser beam actually. So when the laser beam shut down, the atom drops exactly at the same time. Mm-hmm. Well. If you really want to be picky, you could say that there is a light propagation between the two, but you know, up to a few tenths of nanoseconds, it's the same. Yes.
Thank you for your attention.
Yeah.
I take this pause as an occasion for me to thank everyone attending this webinar. I know we are very numerous today from all regions from the world, so thank you for being here.
Yeah.
If there are no questions, we can conclude this webinar. Thank you, Camille.
Yeah, thank you, Jean.
It was really a great time with you.
Yeah, me too.
I think we showed great results.
Yeah.
It opens new perspectives, and we are really thrilled to tackle this new project, this new European project.
Yes.
En route to the field demonstration.
Exactly, and I think it opens exciting time for this new device, and yeah, I think we were going to do a great job with all the partners in the consortium. So thank you, Jean, again, and well,
thank you, the team.
Thank you
from iXblue. Thank you for your support, and see you around. Maybe next week, maybe the week after. We are available. Thank you.
Thank you.